There is a specific comment that you can use in order to calculate the magnitude. What is important for us is that what magnitude shows and how we can manipulate this magnitude image in order to get to some conclusion. For example, here is another example. You have a square function. You have a square function and we are seeing how the magnitude look like. Can you tell me that what happened a few slides ago? We had an S square and we said that the S square has sink. So the sink looks like this. But I'm showing this one and your sink is in this form. Why?
The absolute value?
Yeah, because this is magnitude. Magnitude is always positive. So the negative part all goes up. The negative part all goes up. Now, if you are... Oh, okay, cool. I wear this t-shirt on purpose. So, you see this repetitive pattern, right? We have this repetitive pattern, and let's say that the frequency that I have is F. The frequency is F. What will happen if I was squeezing these lines closer to each other? Yeah, F would be increased because then I will start to have more of the F. So if it was F before, now the F will become a bigger value, right? The F will become bigger value. So it means that in time, if you start to squeeze your image, your signal, what happens in the frequency domain, it starts to be expanded, right? Because if I squeeze, I am increasing my frequency. It means that if the frequency was here, it will start to go further away, right? So, what would happen if I start to take these lines far away from each other? The frequency will decrease. So if it was F0, it will start to become a smaller number. Here, I have a square, and I start to expand it. And if I'm expanding in time domain, it means that I'm squeezing it in the frequency domain, right? This was the frequency representation. It's like that I have squeezed it. Magnitude, of course, it will increase. We don't care much about the magnitude. What is important is that if you are expanding in time domain, you are squeezing in frequency domain. If you are squeezing in time domain, you are expanding in the frequency domain. So this was the formulas that we cared about the magnitude. Now, I said that, and I have erased it, if we have a discrete signal, in frequency we will have a periodic signal. The course that we have is a digital image processing, so when we are going to the frequency domain, what happens is that we have a periodic representation. So, if it is periodic representation, it means we have one block, and this block starts to be repeated, right? Can you tell me that which block in here do I have to pick? Any block. You can actually, you are not obligated to take this. You can take it from here to here, right? What you have to keep it in your mind is that what is the period, you have to pick up one period. And from where you are picking up, it is totally up to you. This is totally up to you. Here is an example. For example, you can start to take from this minus m over 2 to m over 2. This is one period, or you can start to take it from 0 to m. It doesn't matter what you have to do. This is called shifting. And we will use it when we are talking about the images, how the frequency would look like. Now, if I will get back to this slide after I show you this one. Let's say that we have an image. This is a very simple image that I have. And I take this image and I find the Fourier representation of this image. Can you tell me that what do I see? Read the English caption and tell me that what do I see if I take this image and I try to find the Fourier representation. How does the Fourier representation look like?
No, there's 4 corners. You can see that's the corners.
How does it look like? Yeah?
Do we then have 3 dimensions?
No. 2D, 2D. You don't go to the third dimension. We can read the caption if you want. If this is the, use the caption and tell me this answer. If this is the image in the spatial domain, how do the frequency representation look like?
Periodic.
Yeah.
We have 4 corners.
Yeah. What happens is that we have this, which is repeating it everywhere. Now the question that we have is that, okay, we have a frequency, right? This is the frequency that I'm drawing. As you can see, there is a place which is called 0, right? And then we have 0.1, 0.2, 1, 100, 1.0001. We have lots of values. The question is that, where is the 0? Where is the next value? Where is the next value after the next value? If I am calculating the Fourier representation, this is what I get, where the 0 value is at the top corner, and the next value is in another corner, and so on. So in other words, it doesn't go in a conventional way to say that this is the 0, this is the frequency 1, this is for the frequency 2, this is for frequency 3, and so on. So what happens is that I actually have this one to be repeated a lot. So this is the one that I have. This is the 0 frequency, this is another small frequency, this is another small frequency, this is another small frequency. But I know because this image, this representation, I don't use the word image. What happens is that it is repeating itself. It is repeating itself. So it means that I have the same in here. So these corners are coming here, 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 here. I have it up. I have it in here. So as you can see, if I start to zoom out, I can see that there is actually one picture which have all the small values in here, and as I start to go away from the center, the frequency increased. Because let's say that this was the frequency, the period was n by n, I can actually take half of each of them, so I have a new representation. Can you tell me that there is a 0 frequency now? It's in the center. And as I go away from the center, the frequencies start to be increased. Of course, the value of this one is not being increased in the linear form. But what happens is that the center will have the 0 frequency. If you are using MATLAB in your calculations, there is a comment called FFT2, fast Fourier transform, 2-dimension, which finds you the Fourier representation, which is like this. This is not good. We want it in a way that the center to have 0 frequency. So after this one, we usually apply a comment which is called FFT shift, which, you know, if you have this plot, you are just removing it by half of the frequency, half of the period. So you are looking at one other portion of this plot, because it is repeated everywhere in the plane that you have. So if I do this, actually all these corners comes together. So here, at the center, I have the 0 frequency, and the frequencies start to become bigger, and the magnitude start to become less and less and less. 0 frequency is very important for us, because 0 frequency tells us what is the amount of energy that we have inside that image. Amount of energy inside that image, there was another synonym for it. It is, it shows the illumination. If it is very bright, the amount of energy is high. So if it is very low, the amount of energy is very low. In other words, I will ask the assistant to do this. You can play with this zero frequency, the magnitude of it. If you increase it, you will see that in time domain your image will become brighter. If you reduce it, your image will become darker. So this is one other way, actually a very expensive way of manipulating the illumination of an image. So, do you have any question up to this point? Yeah?
This, when we talk in terms of frequency, it's what's the value has been repeated, not in terms of the wavelength of the.
No, the frequency is being repeated. It's a specific pattern which is start to repeat itself. It is like that you have this Lena, but then you have lots of them. It's like a paradise.
What if there was a circle in the center? What would you see? And
we will see lots of examples. Don't worry. Yeah.
So we're talking about wavelengths and pixel values, right?
Yeah.
Do the waves then correspond to a single pixel or the whole image?
No, it's not a wave. It's like that how many of these signs you have to use in order, and you know that because now we have a plane, so how many of these ones you need to have. If you add it up, you will end up to see that picture of Lena. Or you will end up to see this S square in there. Reality, because we are truncating it, we don't have infinity many, so approximately you will get it. So you can calculate always an error, but this is a very small error which you can neglect. Now, if you look at the image in the frequency, so this is the frequency representation of this one, you can see that the center is very bright, and almost if you go a little bit away, you don't have anything. But the reality is that the value at the zero frequency is very high. The magnitude is significantly higher than the other one. That if you show this one, you are not managing to show the other ones. So in other words, we have huge gap, sometimes matter of 1,000 times difference between the first few and the other ones. So it means that I actually have lots of values, but I cannot simply put them into the window of 0 to 255. How can I correct it? Yeah, we have to use a logarithmic based illumination enhancement, and if you do it, this is actually what we see. So you can see that every place we have a value. In other words, we have infinity many frequency. So these are the same thing, but I just did an enhancement so I can be able to see it. If you want to convert it back, you cannot use this. You have to use this one, right? You have to use this one. Any question?
If you can just zoom into it, or
Yeah, you can zoom. Any question? If you have no question, I have question. And the question is, okay, let's see who is Ryan. Rain. There are lots of black lines.
Yeah.
Why?
Because these are not black lines, these are spaces between them.
There are black lines.
But they are not, they are not like black lines.
Yeah,
between
black
dots.
spaces. So why do we have these black spaces?
Since the image is like the sync function, and
Yeah.
it goes to 0 before the next.
Because,
function.
very correct. Because you know we have like an S square, but in 2D, so it means that the Fourier representation will be synced. And in the sync, we have some part which are positive and some part which are negative. When you see it, the negative part means 0, because we are quantizing it. It means that it will become black, dark. So that's why that we have bright part, dark part, bright part, dark part. And if you notice, the dark regions or the lengths of everything is repeated. We know them. Because we know that what is the region, we know that what is this duration that your sync would be negative. and we have it in the x, look at the x direction, it's in the square, look at the y direction, it's in the square, so it will be actually a surface of the sink. So that's why that we have this repetitive darkness. The darkness comes from the fact that the sink sometimes is negative, and it is repetitive because we know that the zeros of the sink is happening in the repetitive format. So this is something that you need to know. Where are these zeros? I don't ask a question. You can always ask Wikipedia, or there are your computer program which tells you where they are happening. Yeah.
But in terms of like why the representation is not a particular square, but it's more like a rectangle. Like if we look at
Yeah.
how the segment is made, why is that?
Yeah. We get back to your question because you didn't listen to my previous slide. Yeah.
So if we convert the image into the Fourier transformations scale, and so the center pixel of the image will be zero frequency, isn't it?
The center here is the zero frequency. Yeah.
Yeah. Okay. So
What's the question?
I just confused a little bit about the zero frequencies.
The zero frequency is now sitting in the center.
So it's always sitting in the center.
Yeah, we use this shifting.
Yeah.
We use this shifting, so we will have the zero frequency always at the center. Because in the next few slides, we see that if it is in the center, we can define the filters. Now, getting back to the question that Aru asked. Very nice question. Which one has higher frequency? This? Which one, even simpler in English, which one is more repetitive? Here, this direction or this direction? Horizontal. So horizontal is like it has been squeezed. So it means that in the time domain, it will be expanded than the vertical one. So you see, you don't need to calculate it. And the question that I might ask would be like the question that Aru asked. Your justification. That why here we have less repetition compared with the horizontal one. Because if you look at it, we know that it seems that horizontally, if you look at the vertical and horizontal, it seems that the horizontal one is like the expanded, so it means that the frequency domain will be more repetitive, more squeezed, than the vertical one. How much it is, I don't ask the question, you can calculate it. Yeah.
What happens if the square on the spatial image is not in the middle of the picture, but somewhere else?
Yeah, we have a few samples, we will see what will happen. You already discussed this one. So, let's do a little test. This is one image I have. So this is like what you asked in general, now is much bigger, huh? We have lots of squares. We have lots of squares. And then I converted it into the frequency domain. Our book converted it. And then this is what I get. This is what I get. How many frequency do I have in here? 3, 4. I don't know who said 4 and why 4, but yeah, 4, 3, 6. Yeah, maybe. I know why they said 6, yeah. Come on, it's free, you can guess. How many frequencies do we have? All of them. Infinity many frequency, okay? Yeah.
I think we have one.
1. Yeah. 2. So, what's the 2?
The center one and the ones on top and the bottom are the same.
Because I told you that we have this symmetry, right? So it means that the top and bottom one are the one, same, right? The center one is the zero frequency. Zero frequency is average of your signal. And we always have it. We will always have it. So if I say that we always have it and we record it, where is the zero frequency here?
It's 0.
Yes, it's 0. the average of the sine or cosine is equal to 0. That's why that it's 0. You have it, but the magnitude of it is 0. In here, the magnitude is not 0, so you have it. So you always see this 0 frequency. If you don't see it, it means that the average of your signal, which is corresponding to your 0 frequency, is equal to 0. And so we have two frequencies. One is the 0 frequency, which is the average of your signal, and the other one is what we see. The other one is what we see, and it has the symmetry. Now, what I do is, I will squeeze this line, so I will start to have more repetitive pattern. If I do it, if I'm squeezing this, so you have 3 lines, instead of, I don't know, 4 lines, I will have 10 lines. What will happen to the Fourier representation? Yeah, I would see the same, but continue. I'm repeating your sentence as well. The center stays the same, but the other ones will go further apart from each other, right? So it will be like this. It will be like this. Why? Which one has higher frequency? This one has higher frequency. Higher frequency means that you go further away from the center. So this is going further away from the center, so it means that's higher frequency. How many frequencies apart from 0 frequency we have here? 1. Yeah? We know we can actually calculate what is the frequency and so on. If I have this one, look what happens. Why I have the dots like this now?
It's non-symmetric.
Why do I have the line? Why do I have these dots like this? What was the dot look like in the previous image? Vertical. Why it was vertical? The changes happen vertically. So here is diagonal because the changes are happening diagonally. Again, same story. We have only one frequency apart from the 0 frequency, and we can see that as it is. If I squeeze, then you will see that these dots, upper and lower one, they will go further apart from each other and vice versa. And what do I have here? Three frequencies. So, do you know how did I create this image?
You overlap the horizontal one and then turn it 90 and then...
Yeah, it is like this. It is like this. I took this one, or the other one. I rotated 90 degrees. It seems that this one has been rotated 90 degrees, right? And then what I did, I took this one in a spatial domain. I took the rotated version of them in the spatial domain. I added them. Then the outputs were added. Do you know what it is called? It's called what type of transformation? You add your input, your output will be added. It's the easiest way of transformation. It's called a linear transformation. Fourier transform is a linear transformation. In other words, if you have something like this, you can say that, okay, this is the addition of the horizontal and vertical one. I look at the vertical one, what is the result? I look at the horizontal one, what is the result? And I just combine the results, right? And if you combine the result, this is what you get. This is what you get. Now, if you notice, I said that this 0 frequency is very important for us. The 0 frequency shows you how much energy you have. In signal processing or in electrical engineering, usually they say that this is the DC value of your signal. What is the DC value means? It means that you have this sine and you add a battery of 1.5 volt to it. Then this sine will happen in a way that the 0 is at 1.5. We give a DC value, right? We give a DC value. So, let's see that I have this picture. I have this picture. Then, I go to the center, and I just replace the value of the center with 0. So, this center has been replaced, the coefficient of it, whatever it was, to 0. and then I come back to time domain, to a spatial domain, and I look at my image. What I look is this. So what's the observation? It will become very darker. It will become very darker. Now, if I look at the frequency representation, you see that this is the image. So by looking at the frequency representation, you cannot understand what you are seeing. In other words, if I give it to you and I tell you that what was inside the image, you don't know. In order to see what was inside the image, you have to always come back to a spatial domain. Now, if you do a very small change, what happens is that, again, we don't see what happens. We have to come back to a spatial domain in order to see what happens. Now, tell me, what is the observation in here? If I give you this and I tell you that, what do you see in the spatial domain? What would you tell me?
We can say that there might be some kind of lines in a particular.
No, we say that there should be a very strong repetitive pattern in this direction. What it is, we don't know. How are the other things, we don't know, but we know that something very strongly tells me that there should be a repetition in this direction. And we know that it exists. Actually, many other parts are also repeating themselves in that particular direction. So this is what we can say, but what it looks like, we don't know. Yeah?
So, does that mean the frequency domain have a different set of image? But
you cannot comment about the content of image. It can be anything.
So meaning a different image
No.
can have the same.
No. Exactly this? No. It may look the same, but it can be totally different. Because this is one-to-one. You can get this one back. You cannot have exactly the same one and then get something else back. It's a one-to-one function. It's reversible. It's one-to-one. The Fourier representation is unique. If you go to Fourier transform, you can always get back to time domain, because otherwise it doesn't. So by looking at it, you can say that, yeah, it might be another image which has a general tendency like this, but it will not be one-to-one like this. So what we did next was that I killed everything and I just kept this value, and I just kept this value in the center. So it means my Fourier representation was just this dot. Then, if I come back to time domain, to a spatial domain, this is what I see. Do you know what this is?
Square.
This is the square. Very good Hans. You deserve a PhD now. Yeah.
It's the average value.
This is if I average all the pixel values in here, I will get this tone value. But what Hans said is actually very, very good. If you have a line, what is the Fourier representation of a line? A little bit more. For a line, like this constant line, the Fourier representation is train, impulse train, right? Now here, what does impulse train mean? It means that you have an impulse and it is repeating itself infinitely many times. Here it seems that we have a line, right? I mean, we have the surfaces in 2D. So it means I'm expecting to see this impulse train. Where is the train?
Outside of the.
Yeah, it's repeating itself everywhere. So it's actually, this train exists. You just see only one of the blocks. Right? You only see only one of the blocks. Again, we don't care much about that. So what we care is that if you have only this one, you will get the average of the image, which is one single tone value, which is one single tone. So here is another example. We have 4 lines, 4 directional lines, and when we look at the Fourier representation, we will be able to see these directions, right? By looking at this, you see that okay, such a directions already exist. Such a direction already exists. Why? Why? Because each of these lines is just like you have lots of zeros and then you have one magnitude and then lots of zeros. What was this signal? It's a square. What is the Fourier representation of a square? It's a seam, right? It seems that I have one seam-ish in that direction, one seam-ish in that direction, and so on. That's why that you will be able to see. And that's why that you have this black region between the bright parts, right? Now, why it is important? Because if you look at this image, you would understand that, okay, you have some changes which are happening in this direction, not much, because you see, and there are some more changes in the horizontal and vertical region. Not many changes are happening in this direction. Again, it doesn't mean there isn't any, but they are not very strong. I think we can stop here. Yeah?
I have a question. What does that mean that the vertical and horizontal lines of the frequency domain are longer than the diagonal ones?
Oh, okay, good question. It gets back to the same point that Aru asked, which means that you are not listening, I'm kidding, to one particular slide that I have. If it is longer in frequency domain, what does it mean? It's more squeezed in the time domain. So you can see that it's shorter in time domain. Yeah? So that's why that you can see that it's much more expanded. This is again an observation that we can see, but having this observation cannot help us to reconstruct the image without really doing it. So it was, did you get your answer? The line, which is the horizontal and vertical, is shorter lengthwise. If I was drawing the lengths exactly the same, it would be expected to see almost the same.
So the frequency domain is some kind of domain that represents the change of the pixels.
So it shows the frequencies. It shows all the frequencies which are available inside your spatial domain. Because right now, if you have my photo, and I tell you that, can you tell me where is the frequency 100? You don't know. Maybe it's in my eyebrow, my hair, and different places. So it exists in every places. So you don't know. So if I tell you that, can you please go and kill the zero frequency of this image? That is easy. Can you kill the frequency 5 of the image? Then you cannot. Unless that you go to frequency domain, then you know that where the frequency 5 is happened, I just make it 0. If I tell you, Jonas, if I tell you that, don't go to frequency domain, can you kill my zero frequency? Yeah, calculate the average and decrease average from all the pixel values. Then you will get your image without zero frequency. Because zero frequency is something that I can calculate it with a Fourier transform. It is the average of all the image. So you can say that the image without zero, F0 is like your image minus image average. Right? So you can do it without going to frequency. That's why that I changed my sentence to you want to keep the frequency 5. Frequency 0, you can do it without going to frequency domain. Remember, going to frequency domain is not always calculatable. We have numerical analysis which help us. It's very difficult and very expensive. And coming back from this frequency domain to a spatial domain is another hassle, and it's difficult, and again, you may need to use lots of approximation. So it's expensive. However, you will see many of the process we cannot do it in a spatial domain.